Hi guys, this is video 4 in the Introduction to Vectors. The next topic for vectors is a definition called the midpoint of a vector. And the midpoint of a vector is defined as exactly what it sounds like. It's the halfway point from the beginning of the vector to the end of the vector. The way that we compute the midpoint of a vector is we multiply the vector by 1/2. So for example, the vector u equals 7, 2, -8. We would find its midpoint as 1/2 u. So 1/2 times u is equal to 1/2 multiplied by 7, 2, -8. And then recall from scalar multiplication vectors that the scalar, or the constant in front, gets multiplied by all the components. So we would have 1/2 times 7, which is 7/2, comma 1/2 times 2, which is 2/2, comma 1/2 times -8, which is -8/2. And then we can simplify. The 7/2 doesn't really simplify. The 2/2 is 1, and then -8/2 is -4. And that would be the midpoint. If we were to graph both vectors, the original vector u and the midpoint vector 1/2 u, we would see that it is exactly splitting that vector in half. We would also be able to confirm that the length of the vector given by 7/2, 1, -4 is exactly 1/2 the length of the original vector, either using the property for scalar multiplication or directly. All right, the next topic for vectors is combining vectors through addition. If you have a vector u and a vector v, you can add them together either geometrically, as shown here, or algebraically, as we'll do in the next example. So to add two vectors together geometrically, you have to take one of the vectors and translate the vector into a directed line segment that begins where the other vector ends. So for example, in the picture shown here, we're adding the vector u and the vector v together. What we could do is we could take the vector u and translate it up so that it's beginning where the vector v ends. So that's what's shown on the right hand side. We took this, so I can change my pointer. If we took this bottom vector here, we translated it up here. Okay, and then the addition of u plus v is the vector that we would get by beginning at the start of the vector v and going to the end of the vector u. Be that straight line there. Now we know that order of addition for numbers does not matter. We know that for numbers, a plus b is the same as b plus a. Like 5 plus 3 is the same as 3 plus 5. They're both 8. For vectors, we have a vector property that u plus v is the same as v plus u. So what we could do is, instead of translating u upward, we could translate v to the right. So we could have done this. We could have taken this vector here and shifted over to the right, so it was like this. So it starts where the vector u ends, and then construct u plus v by starting at the initial position for u and going to the final position for v. And we would get the same resultant vector, the same u plus v that we have on the right hand side picture. Okay, so that just confirms that the property that we had for numbers, that the order of addition does not matter, that property, which is a very nice property, is retained for vectors. Now algebraically, the way that we add vectors is we add them by components. If we're adding u plus v, then the component of the new vector is going to be the x component of the new vector is going to be the x of the first plus the x of the second, and the y component is going to be the y of the first plus the y of the second. And if it's a 3D vector, then the third component, the z component, will be the z component of the first vector plus the z component of the second vector. So an example is given below. The vector v is given with 1, 2, 3, and the vector w is given by -1, -4, 5, and we're asked to find v plus w. So I'll write that in, that v plus w creates a new vector 1, 2, 3 plus -1, -4, +5. We add them component by component, so 1 plus -1, comma, 2 plus -4, comma, 3 plus 5. And then add the pieces. 1 plus -1 is 0, 2 plus -4 is -2, and 3 plus 5 is 8. And that'd be our resultant vector. If we were to draw in 3D the vector 1, 2, 3 and the vector -1, -4, -5, and then translate one of them, just the way we did in the last slide, construct the vector that goes from the beginning of one to the end of the other after we've done the translation, we would find that that vector is described by this 0, -2, 8. Okay, taking the negative of a vector. To take the negative of a vector, what happens is that the original vector size, or length rather, I should say length stays the same, but its direction is opposite. So if let's say the vector was originally pointing straight to the right and it had a length of 10. If we take the negative of that vector, it's now going to point straight to the left. We'll still have a length of 10. So the way that this is described in the language of the course, the language of the textbook, is we would say that the negative vector has the same magnitude but the opposite direction. In component form, so that's the graphical form, in component form the negative of a vector is obtained just by multiplying each component by -1. So if the original vector is ABC, then the negative of that vector is going to be -A, comma, -B, comma, -C. To subtract two vectors, so to subtract one vector minus another vector, unlike addition, order matters, and that's the same as for numbers. 3 minus 5 is not the same thing as 5 minus 3. One is the negative of the other one, and vectors have that same property, so we do have to respect the order of that subtraction. The way that we can picture what subtraction is we can picture first taking the vector u and the vector v and flipping, so reversing the direction of the one that's being subtracted. So if it's u minus v, we'll take the vector v and flip it so its direction is reversed but length is the same, and then add them together. So translate one of the vectors so that it starts with where the other vector ends, and then draw a new vector that goes from the beginning of the first to the end of the second, and that would be the resultant vector of that subtraction. So it's a two-step process. Step 1, reversing the direction of the vector being subtracted, and then step 2, or actually three-step process. Step 2, translating that vector being subtracted, and then step 3, creating the new vector that goes from the beginning of the first to the end of the second. Now to subtract them algebraically, it's far easier. We don't have to do any flipping or anything like that. We just directly subtract the components. So u minus v is going to be 4, 5, 6 minus 1, -2, 7. So we have 4 minus 1, comma, 5 minus -2. You gotta be careful to double negatives. And then 6 minus 7. Same as with numbers. So 3, 5 plus 2, 7, and 6 minus 7, -1. Put a little note here that v minus u is equal to the negative of u minus v. The order matters, and it matters in this way. You can confirm this is the case by doing the example that's above, just reversing that subtraction and confirming that the answer is -3, comma, -7, comma, +1. Yeah. Okay. So another little odd, I guess this falls under the category of odds and ends. It's a convention that we adopt for vectors in 2D and vectors in 3D. We have these special vectors called I and j with little arrows on them to indicate that they're vectors. They are basis vectors or unit, I shouldn't say, I have to be careful of the language. They're unit vectors. They're vectors that have a length of 1, and they only travel in one coordinate direction. So in 2D, the vector I travels only in the x direction and it has a length of 1, so its components are 1, 0. The vector j travels only in the y direction, so its components are 0, 1. In 3D, we have the z direction, and we have a third component for all the vectors. So I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. What these vectors are used for is they're used to construct the vector objects without using vector notation, or sorry, without using the bracket comma notation. It's an alternative way to construct a vector. So for example, the vector 5, -2, it consists of going 5 units to the right and 2 units down. So what you could do is you could say, okay, how many I vectors do I need? Well, I need 5 of those. Each I vector takes me 1 unit to the right, so I need to go 5, so that means I need 5 of them, so 5i. And then how many j vectors do I need? Well, I need to go 2 units down, so I need -2 of those j vectors. So that vector, 5, -2, can be constructed from 5i minus 2j. And then in 3D, if we have a vector 5, 0, 7, we can construct that vector as 5i plus 0 times j plus, oh, there's a typo. I gotta fix that. Plus 7 times k. I'll put in the 0j there. There's 0j vector. If you want to write out a coefficient for each of the I, j's, and k's. So what follows is just a extension of that type of a request. Let's construct, instead of taking the vector that's already formed and expressing it in terms of i's and j's, let's take a vector that's expressed in terms of i's and j's and k's and express it in their usual format. Now, one thing that you have to keep track of carefully when you're working with vectors i's and j's and k's is inferring the dimensions. If all you see is the vector I, that's ambiguous because it could be the I vector in 2 dimensions, or it could be the I vector in 3 dimensions. So you got to look for clues. In example A, you see the vector I plus the vector 3k. If this operation is defined, then it must be the case that vector I is in 3D, because k only exists in 3D. It doesn't exist in 2D. So this must be the negative of negative of 1, 0, 0 plus 3 times 0, 0, 1. It must be the case if we're being asked to add them together. Okay, so then I'm going to multiply that negative into the bracket. So I have negative 1, 0, 0 plus 0, 0, 3. Oh, too many zeros. 3. And then I'm going to add the components together, first plus first, comma, second plus second, comma, third plus third. So negative 1, 0, 3. Okay, next one. But before we put anything down, do we think, are we in 2D or are we in 3D? And there's no k. And we're adding a vector 4, 4, which is in 2D. So if this operation is to be defined, then I and j must be in 2D. Okay, so let's write those in now. We have 2 times the vector I, so 2 times 1 comma 0, minus 3 times the vector j, 3 times 0 comma 1, plus 4 comma 4. So multiply the constants, the scalars in, 2 comma 0 minus 0 comma 3 plus 4 comma 4, and then combine the components. So 2 minus 0 plus 4, we have 6, and 0 minus 3 plus 4, so negative 3 plus 4, we have positive 1. So that would be our resultant vector, 6 comma 1. Now the last question here asks us to construct this maybe scary looking expression, a length of u multiplied by the vector I minus the length of I multiplied by the vector u. So are we in 3D or are we in 2D? That tells us we're using the vector u from part A, which was 3D, so we must be in 3D. Let's get the ingredients. What is the length of u? The length of u is the square root of the sum of the square of the components of u. So square root of negative 1 squared plus 0 squared plus 3 squared. So the square root of 1 plus 0 plus 9, which is a square root of 10. And we need the length of I. So the length of I, that's the square root of 1 squared plus 0 squared plus 0 squared. Since this vector is in 3D, it has those 3 components. We get the square root of 1 plus 0 plus 0, which is the square root of 1, which is 1. Okay, and then we're going to use these ingredients inside our construction of the vector w. W is equal to the length of u, which is 10, inside the square root, times I, 1, 0, 0, minus the length of I, which is 1, times the vector u, negative 1, 0, 3. Okay, and I'm going to multiply the constants in. So we have root 10, comma 0, comma 0, minus negative 1, 0, 3, and then we can subtract the components. So we have root 10 subtract negative 1. So square root of 10 plus 1, making sure that that plus 1 doesn't end up inside the square root. You can't bring it in. You can't call it the square root of 11. It's not true. Comma 0 minus 0, comma 0 minus 3, so negative 3. That'd be your answer. I'll put a little comment here so you don't get tempted to do something bad. Note, the square root of A plus the square root of B is not equal to the square root of A plus B. You're not allowed to merge them in that way. It doesn't work. Do not combine. All right. What's left is just a description of several vector properties that you're not going to be asked to prove, and I'm not going to prove them to you. They're certainly fairly simple, or most of them are fairly simple. I think maybe all of them are simple to prove. So the first property is that the order of addition of vectors doesn't matter, that u plus v is the same as v plus u. The way that you would prove that is you would construct a general vector u, u1, comma u2, a general vector v, v1, comma v2, add them together in both orders, and then use the property that the order of addition of numbers doesn't matter to say that the order of addition of vectors doesn't matter. Formally, this is called commutativity, that the addition of these objects is commutative. The next property is if you add 3 vectors together, the order in which you add those 3 doesn't not matter either. So u plus v plus w, you could begin by adding u and v together and then adding that result to w, or you could start by adding v and w together and then adding that result to u. Or you could add, let's see, u and w together and then add v. This is called associativity, and this property also exists for numbers. 5 plus 3 plus 7 is the same as 3 plus 7 plus 5, or 3 plus 5 plus 7. Doesn't matter in which way you construct that addition. The next property is that adding the 0 vector to a vector does not change the first vector. So u plus 0 is equal to u, as long as the 0 vector has the same dimension. So if u is in 3D, the 0 vector has to be in 3D as well. Otherwise, the operation is not defined. All right, next property on this slide is that the vector u plus its negative will always give you the 0 vector. This is a similar property to the number property, like 5 plus negative 5 gives you 0. Next property has to do with multiplying a vector by two constants. So you take a vector u and multiply it by a number d, and then afterwards you multiply that resulting vector by another number, c. Well, you could have first multiplied c and d together and then multiplied that number by the vector u, and you'd get the same result. Next property is if you have, now sometimes these properties are used in the opposite order in which they're written. So maybe you have a constant times u plus another constant times u. So I'll write this as an example. Let's say you have 3u plus 5u. And you want to construct that vector addition. You can multiply u by 3, you multiply u by 5, and then add them together, but that's extra work. What you should do is you should say, well, this is just going to be 3 plus 5 times u, which is 8 times u. If you want an example for the above, say we're asked for 10 times 1/2 times u. Or I'll make it even worse. I'll say it's, no, I'll do 10. 10's fine. 10 times 1/2 u. Well, instead of multiplying u by 1/2 first, you could say, well, I'm just going to multiply the 10 times 1/2. So 5. And then multiply that by u. Okay, and then the next property on here is if you're adding two vectors together and multiplying by a constant, that's the same as multiplying each vector by a constant and then adding them together. So as an example, say you have, it has to be the same constant c, so say we have 3u plus 3v. It might be easier to write this as 3 times u plus v, because 3u involves larger numbers than u, and 3v involves larger numbers than v. The exception would be if you have fractions. Maybe it makes, if you have, let's say, 1/3 and 2/3 inside u and or v, maybe you're better off multiplying by the 3 first before you're adding them together, and then you don't have to worry about the common denominator issue. So a lot of the time, these properties aren't about testing, do you know your property, but they're about the ability to exploit these properties to simplify the calculation. And which property that you want to use where will depend on the details of the calculation you're trying to do. Okay, and the next set are fairly intuitive, I think. The first one says that if you multiply a vector by a scalar 1, the vector doesn't change. That's a nice property, just like numbers. Multiplying a number by 1 does not change the number. Multiplying a vector by -1 gives you the negative of the vector. We've already been doing that. That's how we've been treating vector negatives. And then the last property is if you multiply a vector by the scalar 0, you get the 0 vector. So it's important that that first one be a scalar 0. And then the output is a vector 0. Okay, and that's it. The last bit is for you to do. This is a practice quiz. This gives you a little bit of heads up about potential question types that could show up on a test or show up on a quiz. You're asked in all of these to identify which statements are false. So you say, maybe that first one's false because I'm adding a 3D plus a 3D to a 2D. And even though the components all sum up to 0, I don't have a third component inside that third vector. I just have 0, 0. I don't have 0, 0, 0. So the dimensions don't work. So I'm telling you the answer for the first one. The first one's false. And if it's false, explain why. So the explanation is that that third vector doesn't have the same number of components as the first two vectors. You have to do something similar for the rest of them. So if it's false, explain why it's false. I'm not going to post the solutions. I want you to post the solutions. Post them to the L forums if you want. This is optional. You're not going to get marked on this. But you're better off learning how to answer these types of questions because you're going to face them on the tests. Let's see if there's anything else to pick on here that's different. Oh, yes. So there's sometimes questions like F that are not as simple to answer. The length of u minus v is always less than or equal to the length of u plus v. So you might look at that and you might convince yourself that that makes sense. But in order for this to be true, you must not be able to find one case that disagrees with the statement. So this is the idea of a counterexample. If I said there is no such thing as a, let's see, if I said there's no such thing as a cat that has orange fur, no such thing, how would you prove to me that I'm wrong? Well, you would bring me a cat that has orange fur. Or if I said all apples are red, every single apple that exists is red, you would prove me wrong by bringing me a green apple or a yellow apple. That's what you have to do for question F. I'm going to tell you it's false. Okay? Now on a test you'd have to figure that out, that it's false, that u minus v is not always less than or equal to the length. The length of u minus v is not always less than or equal to the length of u plus v. But you have to bring me an example. Bring me an example of a vector, or two vectors, u and v, that when you subtract them, the length is not less than the length that you would get if you added them. So some of the questions will, if you want to prove them false, will require bringing a counterexample, and other questions you can say they're false because they don't match a definition. Anyway, if you need help or you're stuck, post on the forums. See you next time.